Hello everyone. So in this video we're going to be talking about maxima and minima and using the first and second derivatives to find them. Now maxima and minima are of course points that are the maximum or the minimum of a graph. Now it can be a relative maximum, a relative minimum, or an absolute maximum or an absolute minimum. We will go into those terms, to the meaning of those terms as we advance in the video. Now, the first thing that we have to remember is that at a point on the graph, which is a minimum, for example, here, the tangent line to that minimum point is a line that has a slope of 0. That means that the derivative of that function at that point is equal to 0, right? Because remember, the derivative gives us the slope. And this applies to both these cases, the minimum and the maximum that we can see in these parabolas. So precisely, that is the concept that they want us to use in example 12.12, as we're going to see. So they say, using differentiation, find the coordinates of the vertex of the parabola with the equation y equals x squared minus 8x plus 14. So remember that normally we would just use minus b over 2a as a formula to find the x coordinate of the vertex. But here instead, we're going to use the derivative. So we're going to find dy dx. This is using the Leibniz notation, right, which is just finding the derivative of this expression, x squared minus 8x plus 14. And this is going to equal 2x minus 8. Now, because we want to find a minimum, we equal this to 0. So 2x minus 8 equals 0. And solving for x is equal to 4. So that's going to be the x coordinate of the vertex of the parabola. That means that I need to plug this into f of x. A common mistake is that people plug it into here again and get 0, and then write that down as the coordinate. So you have to be careful with that. So basically, we really need to find the y value when x is 4. So we need to do this. And if we do the math, that's going to give us -2. So that means that the vertex of the parabola is at coordinates 4, -2. So in the next slide, what we have is precisely the graph of the function. Notice that here is the vertex, and these are the coordinates of the vertex. And it's a minimum, like we said before. Now, I knew it because it was a parabola where a is greater than 0. But normally, in other types of functions, we're going to have to do some testing. And once we get this critical point here where the slope is 0, notice that we can use the derivative to find out what the slope is here, the right of that value in this case, and then here to the left of that value. So we could see that for the derivative of x, we're going to get a negative slope, and then here for the derivative, we're going to get a positive slope. So that tells us that it's increasing here, right? Because the slope is positive, and it tells us that the graph is decreasing here because the slope would be negative. Notice that that is explained here. Slope changes from negative to positive as x increases. So that's something we're going to use in the following problems. Okay, so here we are on example 12.13, and they say consider the function f of x equals 2x cubed plus 3x squared minus 12x minus 4, x belonging to the reals. A, find the coordinates of any stationary point. So remember that the stationary points are the points where you have this situation. So that's what we're going to use, the principle we're going to use for A. So let's find the derivative of f of x. And we're going to have that it's 6x squared plus 6x minus 12. And then let's equal it to 0 to find the coordinates of those stationary points. So we equal this to 0, and we can factor, right? Let's factor out the 6. We get x squared plus x minus 2 equal to 0. And the factors of this have to be 6, and then we have x plus 2 times x minus 1. X plus 2 times x minus 1. That means that the solutions are x equals negative 2 and x equals 1. So then by plugging those values in the original function f, we get that f of minus 2 gives us 16, and f of 1 gives us negative 11. Therefore, the coordinates would then be negative 2 comma 16 and 1 comma negative 11. Now notice that this gives us a hint of being a maximum, and this gives us a hint of being a minimum. But let's use the derivative to classify these points, these stationary points. And for that, we're going to need a table. So I'm going to get rid of all this, and I'm going to draw a table. Okay, so we have that x equals negative 2 is a stationary point, and so is x equals 1. So let's find out what happens between these values and before them and after them as well. Okay, so for that we need to use the derivative, right? So remember that the derivative was equal to 6x squared plus 6x minus 12, and we simplified it into 6 times x plus 2 times x minus 1. So we're going to use this to determine the sign of numbers that are less than negative 2. So let's plug in something like, say, negative 4. Okay, so if we plug in negative 4 for x, what do we get? We get 6 times negative 2 times negative 5. And notice that this is going to give us something positive, right? Because this equals 60, which is positive. So that means that here the slope is greater than 0 for all these values that are before negative 2. That means that the graph is increasing in this interval of the graph. So let's see what's going on between negative 2 and 1. Remember that these are the stationary points. So this is stationary and this is stationary. So let's see what happens between negative 2 and 1. And an easy value to plug in is 0, right? So let's see what happens with 0. So with 0, we're going to get 6 times 2 times negative 1. And notice that this is negative 12. That means that the derivative here is going to be negative. So here the graph is decreasing. So the graph is first increasing, then it gets to negative 2, and then decreases. So let's see what happens at x equals 1, where it's stationary, and what happens after that, right? So let's plug something greater than 1. Let's say 2. All right, so if we plug in 2 for x, we're going to get 6 times 4 times 1, and this equals 24. Therefore, after 1, the derivative, or the slope, is going to be positive, greater than 0. So notice that we have a situation here where the graph is increasing in the interval before negative 2. So from negative infinity to negative 2 for x, the graph is increasing. It reaches a maximum, then it decreases. It decreases to the point 1, where it reaches a minimum, and then it increases again. Very well, so here we are now on example 12.14, where they say for the function f of x equals x to the 4 minus 2x cubed, find the coordinates of all stationary points and describe them completely. So it's basically the same thing we were doing before. First thing to do is find the derivative. So the derivative of that expression is going to be 4x cubed minus 6x squared. And then we need to find the stationary point, so equal this to 0 and factor. So here we can factor 2x squared. And then that's going to equal 2x minus 3. Therefore, the stationary points are going to be where x equals 0 and where x equals 3/2. All right, I'm not going to plug this in the original because I want just to do the table directly this time. So let's draw the table. And we're going to place 0 here as a stationary point. So this is a stationary point. And we have 3/2 here as another stationary point. And we're going to find out if these are maximum or minimum or none. Because sometimes you might have a situation where you have a stationary point, but it's neither a maximum nor a minimum. So let's try with a value less than 0. Let's say x equals -1. So if we plug that into the derivative, notice that we're going to get -10. And that is less than 0. That means that here the function is decreasing. Then it gets to the stationary point 0. Let's see what happens after 0. So let's plug a value between 0 and 3/2. An easy value would be 1. So let's test x equals 1. Now remember that we have to plug this into the derivative, right? So plug it in the derivative, and we're going to get -2, which is, again, less than 0. So it means that in this graph, this is not a minimum because it's going down. It has a stationary point, but then it keeps going down. So this cannot be a minimum, and it cannot be a maximum either. Okay, so then it gets to 3/2 where it's stationary, and let's see what happens after 3/2. So let's plug in something like x equals 2. So plug that in the derivative, and we're going to get that that equals 8, which is greater than 0. So that implies that this is an absolute minimum because it reaches this point, and then the graph has a positive slope, meaning that it's increasing. So here we have the graph of the function y equals x to the 4 minus 2x cubed, which is the one we just solved. The first thing we have to look at is the stationary point. So at x equals 0, we have a stationary point, and then the other one right here at x equals 3/2. Notice that the tangent at these points to the line is just going to be horizontal. So that's where we know that you have a point where you either have a minimum, a maximum, or, like occurs here, something called a point of inflection. Now, what's a point of inflection? A point of inflection is a point on a graph where you have a change in concavity. Notice that here the graph is going down. As you can see, it's decreasing, but also you can see that the concavity is upwards. Then it reaches the inflection point where the slope is 0 and changes the concavity to a downward concavity, although the graph is still decreasing. Then here we reach a minimum, and the graph increases, just like we discovered using the first derivative test. Very well, so here we are now with example 12.15. And again, apply the first derivative test to find any extreme values for this function. So this is exactly the same as before. First of all, let's find the derivative. So the derivative of f of x is going to be 12x squared minus 18x minus 120. I'm going to factor this, and notice that this can factor as 6 times 2x squared minus 3x minus 20. And we can factor this even more, right? Because this is the same as, so let's use the equal sign here. This is the same as 6 times 2x plus 5 times x minus 4. Okay, since we have to equal this to 0 to find the stationary points, we're going to see that one of them is minus 5 halves, and the other one is going to be 4. So I'm going to build the graph or chart table based on these two values. And we're going to see the behavior of the function. So let's plug in a value in the derivative that is less than negative 5 halves. So let's say negative 3. So if we plug that into the derivative, plugging negative 3 into the derivative will give us 42. And 42 is greater than 0. So that means it's increasing. So it's increasing. It reaches a stationary point. So let's see if it keeps increasing or if it goes down. So let's plug a value between negative 5 halves and 4. And the easiest one is always going to be 0. So let's plug in 0. So that into the derivative will give us negative 120. Notice that that means that after negative 5 halves, the graph starts going down. So that means that this is a relative maximum. Okay, so that probably means that this is a relative minimum for 4. But we're going to verify that by plugging in something greater than 4. Let's say 5. So if we plug that into the derivative, it's going to give us the slope. And the slope there is 90, which is greater than 0. So that means that it's going to be increasing. So this here is a relative minimum. And therefore, we have found the extreme values for this function. So in the following slide, you're going to find examples of what we have been exploring. So here we have a graph that is increasing, then it gets to a stationary point and decreases. Notice that the first derivative indicates where the graph is increasing and where it is decreasing. This is for a maximum, and the same thing for a minimum. You can see here the decrease where the derivative is less than 0, a minimum where the derivative is equal to 0, and the increase where the derivative is greater than 0. Here's a case where you have a point of inflection and not any extreme. So that's why it says no extreme. You have a change in concavity, though, because you have a concavity here that is downwards. You have the point of inflection where the slope is 0, and then it keeps increasing. Therefore, what you have is a change in concavity, as you can see here, because here the concavity is upwards, and before it was downwards. On the right, we have cases where the domain is restricted. So notice that a point C here is a restricted domain. In this case, for x, from C to infinity. So you can say that this would be a relative maximum here, because after point C, the graph is decreasing, as indicated also by the derivative. This is the same thing, but backwards, right? You would have a relative minimum here at point C, and then the graph increasing, and the derivative greater than 0. And here, exactly the same, but with C to the right. So we have decreasing, a relative minimum at point C, and here we have increasing, a relative maximum at point C. And notice that the derivatives correspond with the increasing or decreasing of the graphs. Okay, so now we are on example 12.16, and it says a toy rocket is launched upwards into the air. Its vertical position, s meters, above the ground at t seconds, is given by this function here. A, find the average velocity over the time interval from t equals 1 second to t equals 2 seconds. So remember that when you want to find average velocity, that is just the slope of the line between those 2 points. So basically what they're asking us to do is to find s of 2 minus s of 1 over 2 minus 1. So that means plugging in 2 into the function. And if we plug in 2, that's going to give us 17. Minus, if we plug in 1, we're going to get 14. Okay, and that over 2 minus 1, which is 1. So 17 minus 4 is 3. So 3 meters per second. 3 meters per second would be the average velocity between those 2 points. Okay, so for part B, they want us to find the instantaneous velocity. Now remember that whenever you see the word instantaneous velocity, or the words instantaneous velocity, it means derivative. So let's find the derivative of s. So the derivative of s is going to be negative 10t plus 18. And now what we have to do simply is plug in 1. So that means do s derivative of 1, and that's going to equal 8. So that means that the instantaneous velocity after 1 second, or at 1 second, was 8 meters per second. Okay, so for part C, they ask us to find the maximum height reached by the rocket and the time at which this occurs. Okay, I'm going to do it backwards. First, I'm going to find the time at which this occurs because I think it's easier. And that time is when the slope is 0, because that would be the maximum. So minus 10t plus 18 is equal to 0. So solving for t, we're going to get that this equals 1.8. So after 1.8 seconds, it reaches the maximum. Okay, so in order to find the height it had, the maximum height, just plug this into the original function, right? So we need to do s of 1.8. And s of 1.8 will give us approximately 17.2 meters, rounded to 3 significant figures. Okay, so now what we're going to see is the relation between a function and its second derivative. Now we're not going to read all this, we're just going to go to some graphs that we have over here, and we're going to briefly explain them. So if we look at the first graph to the left, we can see that this is the position function. Notice that the rocket started at 0, then over a certain time interval went up to a maximum height, and then just went back down. If we do the first derivative of the position function is going to be the velocity. So this is the function for the velocity. Notice that it's a constantly decreasing velocity. So it was decreasing since the moment the rocket took off. It reaches 0, and then it continues decreasing. Very well. Then if you do another derivative, which would be the second derivative, so the derivative of velocity, which is the second derivative of position, gives us something called acceleration. Now if we do the derivative of this, notice that it's negative 10, and it's a constant acceleration, which makes sense in this case. So you see the graph of the acceleration, which is just a constant line at negative 10. Why is that? Well, because you have a constant deceleration, actually, a negative acceleration, which is due to the force of gravity. Remember that the force of gravity is approximately negative 10 meters per second squared. Okay, everyone, so here we are on example 12.17. And it says an object moves along a straight line so that after t seconds, its displacement from the origin in s meters is given by s of t equals this. Find A, expressions for 1, the velocity, and 2, the acceleration. So let's start with velocity. Now remember that velocity is going to be the same as the first derivative of the displacement function. So that means it's going to equal negative 6t squared plus 12t. So that's going to be the velocity function. As for acceleration, let's recall that acceleration is the same as the derivative of velocity, which is also the second derivative of the displacement. So we're going to get that the acceleration function is minus 12t plus 12. Okay, and then for part B, they want us to find the initial velocity and the initial acceleration when time was equal to 0. So for number 1, they want the initial velocity at time equals 0. And notice that that's going to give us 0. So that's 0 meters per second. And then for part 2, they want us to find the initial acceleration when time was 0. So notice that's going to be 12 meters per second squared. Okay, so once we have this, A and B, let's work on C. So I'm going to erase this, and we're going to be working on letter C. Okay, so for part C, they're asking us to find 1, the maximum displacement, and 2, the maximum velocity for the interval between 0 and 3. Now this is important. You'll see why in a bit. So the maximum displacement. So let's look at the maximum displacement. Now we know that the displacement formula is equal to minus 2t cubed plus 6t squared. Now remember that in order to find the maximum or the minimum of displacement, we need the derivative. But the derivative, we already found it. It's the velocity formula. And the velocity formula is minus 6t squared plus 12t. So in reality, this is what we need. And we need to find out, first of all, when this equals 0, because that would be the maximum for the displacement, or the minimum, depending. Okay, so let's solve for this. And notice that we can factor out minus 6t. So then this would be equal to negative 6t times t minus 2. And we also need to take into account 3 because that's the last second in the time interval. So what we need to do is test values between these 3 points, because 0 is the starting point, and also it's going to be where the slope is 0, meaning that it can be a minimum or a maximum for the displacement. Most obviously, probably a minimum, right? So at 2 seconds, you might have a maximum, and then we have to see what happens before 3 seconds, right? Okay. So let's test the value 1. So what was the velocity at 1 second? And if we plug that in, it's going to give us 6. So notice that 6 is greater than 0. That means that the displacement was increasing. With a positive velocity, you have a displacement that is increasing. So here, you have a stationary point, and then let's see what happens after that. So let's use something between 2 and 3, so 2.5. What was the velocity at 2.5? Let's plug in 2.5 in the velocity function. And if you do that, you're going to get negative 7.5. Now this is less than 0. It means that the displacement was decreasing. Okay, so that means that the maximum displacement occurred at t equals 2 seconds. So for t equals 2 seconds, let's find the displacement. And if we plug that in there, we're going to get 8. So that means that the maximum displacement was 8 meters at 2 seconds. Okay, so let me get rid of this a little bit here. Let me get rid of this. And let's work on the maximum velocity. So we're doing part C, and in C, we're doing 2. So maximum velocity. Now let's recall that the velocity formula or function is going to be negative 6t squared plus 12t. And we're going to need the derivative of this, which is the acceleration. And as you know, the acceleration formula or function is minus 12t plus 12. So we need to find the extrema, right? When the velocity reaches a maximum or a minimum. So that occurs when but when acceleration is 0. Okay, so this happens at time equals 1. We can see this obviously as the solution to this equation. We also need the other 2 points, critical points, which are going to be 0 and 3. Why? Well, because that's the interval, right? Okay, so next what we need to do is plug in some numbers that are between these values to see what's going on with the graph of the velocity. And we can use the acceleration because the acceleration is the derivative of velocity. So what happens at 0.5 seconds with the acceleration? So at 0.5 seconds, if we plug that in there, notice that we're going to get 6. And 6 is a positive acceleration. That means that the graph is increasing for the velocity. Then there's a stationary point at time equals 1 where we have an acceleration of 0, so therefore a maximum probably of the velocity. But let's see what happens after 1 second, between 1 and 3 seconds. So let's use 2 seconds. So what was the acceleration after 2 seconds? Again, let's plug that in and notice that we're going to get negative 12, which is less than 0. That means that we have a negative slope for the velocity because the acceleration is negative. Okay, so that means that 1 is actually a point where the object reaches a maximum velocity. And we can calculate that maximum velocity by simply plugging in for time equals 1 in the velocity function. And notice that we're going to get 6. So that means that the maximum velocity was 6 meters per second at time equals 1. So precisely in the next slide, what we have is a graphical representation of the situations in the previous example. So this first graph that we have to the left is the displacement function, as we can see here. And notice that the displacement function reaches a maximum precisely at 2 seconds, as we found out. And we used we used velocity to determine the maximum displacement. Remember that here, the velocity was 0 because the velocity being the slope of displacement is 0 at this maximum point. And then we tested some values before too to see if the velocity was positive, as indicated by, for example, this tangent here, which we can see has a slope that is positive. Likewise, after 2 seconds, we have a negative slope, or decreasing. So moving to the next chart, we see the velocity chart, and we knew that the maximum velocity was, or we found out actually that the maximum velocity occurred at 1, where the acceleration is 0, right? The maximum velocity would be when the slope is 0, but because the derivative of velocity is acceleration, that is when we had that maximum velocity. Now notice that when velocity was 0, that's when we had that maximum displacement. And likewise, when acceleration was 0 here, that means that this is the point at 1 second where you had a maximum velocity. Very well, so this next slide I'm going to use to explain some aspects about the first and the second derivatives. So let's take this curve here on the left, top left. So let's call this f of x. Now recall that when we find the derivative and equal it to 0, we're going to find something like a minimum. Now, interestingly enough, if we do the second derivative and test that same point where the first derivative was equal to 0, and we can use the second derivative as a test for concavity. So it turns out that if the second derivative is greater than 0, then we're going to have a curve that is concave upwards, such as this one. If the second derivative at that point is less than 0, then we're going to have downward concavity. Okay, but what happens in other cases, like the ones that we have here in these other 3 graphs? Now notice that these graphs don't represent maximums or minimums, but rather inflection points, stationary. In this case, this is a stationary inflection point. And something interesting happens here, because for this stationary inflection point, the first derivative would equal 0 there, but also the second derivative. We would have to test values after this point here with the second derivative to see if the concavity is upwards or downwards. But we'll see that. It'll be clearer in an example. Then in other cases, inflection points can be found with the second derivative. So these inflection points will occur where the second derivative is equal to 0. Very well, so here we are now on example 12.18, and it says determine the intervals on which the graph of y equals x to the 4 minus 4x cubed is concave up or concave down, and identify any inflection points. Okay, so I think we have to do this backwards. We should probably identify the inflection points first. And remember that for that we need the second derivative. So the first derivative is going to be 4x cubed minus 12x squared. Then the second derivative is going to be 12x squared minus 24x. So the inflection points occur where the second derivative is equal to 0, recall that. So let's equal this to 0 and solve for x. So here we can take out a common factor of 12x, so that would be 12x times x minus 2. And the solutions to this are 0 and 2. So those are going to be the inflection points. Now, by using these inflection points as a guide, we're going to find the intervals where the concavity is upward or downward. So let's test values that are less than 0. For instance, let's test x equals -1. Then we plug that into the second derivative, right? So plugging in -1 into the second derivative is going to give us 36. Now, because 36 is positive, it means that it has upward concavity. Then let's test the value between 0 and 2. For instance, x equals 1. So if we plug 1 in the second derivative, we plug in 1, we're going to get -12, which obviously is less than 0. So that means the concavity between 0 and 2 would be downward. Okay, finally, a value greater than 2. So that would be, let's say, something like 3. And if we plug in 3 in the second derivative, we're going to get 36 again. And 36 is greater than 0. Therefore, the concavity should be upward. A better way to understand this is by actually looking at the graph of the function. So I'm going to show you the graph and what it looks like. And there you go. You can see the points of inflection, which are 0 and for x equals 0 and for x equals 2. So here is the other point of inflection, 2, -16. And so let's look at the concavity. Notice that before 0, the concavity is upward. Then here it's downward. Then here comes another inflection point. And finally, the concavity is upward. Now, these are things that we're going to need besides finding the intercepts, right? X and Y intercepts, the minimum, the maximum points, to be able to graph a function manually. Very well, so now here we are on example 12.19, and they want us to find any relative extrema for this function. Now remember that extrema means maximums and minimums, not inflection points. So what we need to do is find the first derivative and equal it to 0 to find those maximums and minimums. Okay, so let's look at that. Recall that the first derivative of this function would then be simply doing the power rule, right? So that would give us 15 x to the 4 minus 75 x squared plus 60. Okay, so this would be the first derivative of f of x. Now we equal this to 0 and then try to factorize it. So always start with a common factor. So here you have a common factor of 15, not x though, right? So just 15. So we can rewrite this as x to the 4 minus 5x squared plus 4. And this equals 0. Now notice that this is factorable, right? We can factor that as we would do by inspection. So this would be 15 times x squared minus 4 times x squared minus 1. But this is a difference of squares, and so is this. So we can factor even further. So we can rewrite this as 15 x plus 2 times x minus 2 times x plus 1 times x minus 1. And there it is. This is the total factorization of this. So notice that we have 4 stationary points, right? 4 extrema. And what are they? They're going to be -2, they're going to be 2, -1, and 1. So now, in order to determine whether these points are a maximum or a minimum, because we do know that they have to be either 1 since the derivative is equal to 0 at this point, at these points. So what we have to find out through the second derivative test is the concavity. So let's find the second derivative. Okay, so the second derivative of the function is going to be equal to 4 times 15, so that would be 60x cubed minus 150x. Okay, so now we plug in those points at which the slope is 0, and we plug them here in the second derivative to see if the concavity is downward or upward, right? So let's start with the smallest value. So second derivative test with -2, if we plug that in there, we're going to get minus 180, which is obviously negative. So that means that the function would have a downward concavity at x equals -2. And that means that this is a relative maximum. So -2 is a relative maximum. Now let's put them in order. So let's try -1. Okay, so at -1, we're going to get 90, and 90 is greater than 0. Greater than 0. So that means that the concavity is upward, therefore this is a relative minimum. So at x equals -1, we have a relative minimum. Okay, so next, let's do the second derivative test in 1. And for 1, we're going to get -90. And -90 is less than 0, so that means downward concavity, therefore this is a relative maximum. Okay, and finally, second derivative test with 2, and with 2, we're going to get 180, which is greater than 0. That means upward concavity, so this is a relative minimum.